Module 1, Lesson 3, Regula-Falsi method. For this particular module, we will then discuss how bracketing techniques evaluate your corresponding root. The Regula-Falsi method, the bracketing condition applied for this technique, its derived iterative formula, and sample problems that eventually are solved using Regula-Falsi method. Bracketing techniques are these techniques that eventually sets up two initial values or initial guesses for your root. These particular initial guesses must respectively bracket your corresponding root. The particular method described herein employs different strategies to systematically reduce the width of bracket and hence home in or converge on your root value. One such bracketing technique is known as the Regula-Falsi method. This method is applicable to both polynomial and transcendental function. It is also known as linear interpolation or more often as the method of false position. This technique, much like your previous bisection method, sets up two initial values of your corresponding x. These initial integer values x0 and x1 must have opposite signs of functions in order to satisfy this given bracketing condition. Note that this condition can only be satisfied if both functions are opposite in terms of sign. The product of fx0 and fx1 can only be a value less than 0 if exactly one of these functions is negative while the other function is positive. This is a graphical depiction on how the particular technique works in evaluating for your root. After setting up an initial value x0 in this given graph, which has a negative function fx0, and x1, which has a positive function fx1, we then connect these two particular functions using a straight line, and that straight line will eventually intersect your x-axis. That particular straight line is also known as your second line. This second line is then evaluated using similar triangles in order to come up with the iterative formula for your Regula-Falsi by using this right triangle, which is similar to this right triangle, or using this similar triangle. And upon doing so, you'll be able to derive the formula for your corresponding Regula-Falsi. So first, let's derive the formula using the red right triangle and the yellow right triangle. Thus, it again gives us the iterative formula like this. And if we manipulate then and solve for your corresponding function x2, you'd end up with this iterative formula for your right triangle. However, if you use the red triangle and the blue inverted right triangle, you would then end up with this respective equations. And if we evaluate then x2 for your given equation by manipulating your equation, you would now end up with this other iterative formula. You could technically use either formula to solve for x2, and both answers will eventually have the same value. Now that we've set up the iterative formula for the Regula-Falsi to be either this formula or this formula, we could then proceed on solving for x2. After solving then for your new root estimate x2, we substitute x2 to your given function f of x to obtain fx2, much like your bisection method. And again, if your fx2 is not equal to 0, this implies that your calculated root x2 is not your root. Hence, we replace one of the bracket values, either the positive function limit or the negative function limit value of x. If fx2 is greater than 0, then we replace positive function limit value of x with x2. However, if fx2 turns out to be less than 0, then we replace the negative function limit value of x with x2. This process is then repeated over and over until your respective terminating condition is satisfied, which is usually, again, based on an error criteria, either using the absolute error criteria or the regular residual error using the relative error criteria. This is one such example in using the said technique. As mentioned, the technique can also evaluate polynomial or transcendental function. Let's try to evaluate then the root of this given same function that we have previously solved using bisection method, but now let's try to evaluate the root using Regula-Falsi method. We then first equate your given function to 0 and then establish initial integer limit values for your x0 and x1 by tabulating possible initial integer values. Note that this particular integer values were simply substituted to your given function f of x, thus ending up with the following values. And again, you would notice that this initial values stated here are the initial integer values closest to your root position, having an initial integer value that gives us a negative function and an initial integer value that gives us a positive function. Therefore, your first iteration would now contain the following initial integer values. Substituting them to your iterative formula would give us this solution for x2 with a value equal to 4.2308. Substituting 4.2308 to your function gives us an fx2 value now having this solution with a value of negative 1.638. We then repeat the process since your function fx2 is not equal to 0, therefore your respective x2 is not your root. I then replace x0 with x2. On the second iteration then, my given values for x0 and x1 are as follows. And note that this initial values x0 and x1 still follow my bracketing condition. Hence, the root is still between x0 and x1. Thus, you'd end up with an x2 solution equal to this with a value 4.2890. Substituting 4.2890 to your function gives us a value of negative 0.3947. Obtaining now its absolute error as our terminating criteria gives us an error equal to 0.0582. We then replace, again, x0 with x2 since our terminating condition is not satisfied. On the third iteration then, this now would be your values for x0 and x1. Note that these values still satisfy the bracketing condition. Therefore, we simply solve for x2 using this solution based from our iterative formula, ending up with a value 4.3028. Substituting 4.3028 to your function gives us a value of negative 0.0911 with an error difference equal to 0.0138. Note that this error still does not satisfy the terminating condition. Therefore, we replace x0 with x2. On the fourth iteration, this now are the given values for x0 and x1. We then establish that this initial values still satisfy the bracketing condition, therefore the root is still between x0 and x1, which gives us an iterative solution for x2 equal to this solution with a value of 4.306. Substituting 4.306 to your function gives us a function value fx2 equal to 0.0203 with an absolute error this time of 0.0032. Note that this terminating condition still does not satisfy your respective root. Therefore, we repeat the process by replacing x0 with x2. On your fifth iteration, you would now have this given values for x0 and x1. Your x2 now would be evaluated like this using the iterative formula, ending up with this solution and a value 4.3067. Substituting 4.3067 to your function gives us a function value fx2 equal to negative 0.0047 and an absolute error this time equal to 0.0007. However, this error still does not satisfy your terminating condition. Thus, we again replace x0 with x2 since your function fx2 is negative. Then, on the sixth iteration, this now are your respective given values for x0 and x1. We then evaluate again x2, and it should have this given solution with a value 4.3069, ending up with a function fx2 value equal to negative 0.0003 according to our solution, and an absolute error equal to 0.0002. on which we eventually found that this particular error criteria still does not satisfy our terminating condition. We then repeat the process by replacing x0 with x2. So on the 7th iteration, we end up with these values for x0 and x1. Note that these values still satisfy your bracketing condition. Hence, solving for your root, you'd end up with this solution, ending up with a final value equal to 4.3069 for your x2 again. Thus, your error and your function fx2 would simply be, again, negative 0.0003 and an absolute error value of 0. Thus, we then terminate the process, showing that this particular technique proves to be more efficient in solving for your root value, which is 4.3069, as compared to your bisection method, which eventually took around 13 iterations before the process eventually terminates. So much like your bisection method, we could summarize the result for your Regula-Falsi in a tabulated manner like this, showing the values for our root estimate x2 for each iteration and showing the important function values fx0, fx1, and fx2 that are needed in solving for your root estimate x2. This ends Module 2, Lesson 3.